Second video. Now we're getting into how to use identities with reviewing identities with Trig, and also using them ultimately to solve a problem like that number 5 down there, solve this thing on the interval 0 to 2 pi. So identities that we should be able to keep track of. These first 4 right here we call the reciprocal identities. I've already referred to a number of them in terms of solving some of those trig expressions that you already watched. You should have already watched a video on. Getting into some of these over here to the right side of the page, even odd properties of trig functions. The idea here is these are supposed to be shortcuts. They're supposed to save us time. So we're supposed to be able to look at these and go, all right, if somebody asked me to find, for example, the sine of negative 90 degrees, okay? Now, we already did a problem where in the previous video where we were supposed to be rotating with negative 90 degrees, we were supposed to be rotating, we know, clockwise. So if that's the case, the only thing what we're trying to figure out here is, if I've got an angle and they tell me to rotate through a positive angle, I know I'm rotating that way. If they tell me to rotate through a negative angle, I know I'm going to rotate that way. So the only difference is the direction that you go. Now, I said in the previous video that the idea with every trig function is you got to come up with a reference angle and a quadrant. So these even and odd properties, when I'm dealing with a negative on an angle, what that really means is I'm rotating a different direction. So what you need to think about is, how do these reference angles compare? Well, that sine of the opposite of theta and the sine of theta, those reference angles are exactly the same. The truth of the matter is, the negative in front of this angle, this negative right here, means I'm rotating it in a different through a different direction in order to come up with that final the final location. So the idea here is, if I rotate sine, let's say we take an example. Let's say I do negative 90 degrees. How does sine of negative 90 degrees compare with sine of positive 90 degrees? Well, negative 90 degrees would mean that I should rotate this thing this direction, and I'd end up being really at 270 degrees, or 3 pi over 2 if you're using radians. And we know that the sine of negative 90 degrees is going to turn out to be negative 1. Well, if I rotate to positive 90 degrees, that means I'm supposed to go the exact opposite direction, and I'm going to end up at 90 degrees itself. Well, what is the sine of 90 degrees? Well, that's going to turn out positive 1. So to make your little comparison right here, the conclusion I want you to draw is, if you're given a negative on an angle, much like this 90, the only difference in the result when you're talking about sine of the opposite of an angle versus sine of an angle is the results are going to switch signs, meaning switch from positive to negative or vice versa. So sine of the opposite of the angle turns out to be the opposite of sine of the same angle, without the negative sign on it. So cosecant will work the same way. Cosine, if you think about this, if I did my exact same example, cosine in, for example, quadrant number 4 would match cosine in quadrant number 1 if we used the same reference angle. Tangent in quadrant number 4 would be the opposite of tangent in quadrant number 1. And we already demonstrated with sine, sine in quadrant number 4 would be the opposite of how sine would turn out in quadrant number 1. So these even-odd properties are meant to be a shortcut. They tend to throw people off a little bit, but that's meant to be a shortcut and save you some time. Some of these other identities that we have here. Pythagorean identities, these 3. I will tell you, I fully expect people to keep track of this first one, but I need you really to think about how these 2 work. Now, the truth of the matter is they all come from sine squared plus cosine squared equals 1, and that'll be something maybe in class tomorrow we could talk about if you guys want me to show you where they come from and how they work. But the idea would be, when I'm working through some of these things and trying to figure some of these things out, they're just going to be really useful as we go down the road in calculus. We're going to use it a lot. We're going to be dealing with a lot of different things here, and those identities are going to be important. These blue ones would be your double angle identities, and the cosine 2 theta has 3 different versions, but my thought is if I can keep track of one of them, I can use this Pythagorean identity over here in order to rewrite what the other ones are. So let's put these things in action. Let's kind of see what we got going here. So if I'm trying to solve an equation, solve this thing on the interval from 0 to 2 pi, the first thing you got to notice, you can't solve a trig equation unless they're all talking about the exact same reference angle. And we've got two thetas on one side of the equation, and we got thetas on the other side of the equation. And I can't put those things together unless I can get them down to the same result. So cosine 2 theta. We're going to use our double angle identity for cosine to rewrite this thing. So if I rewrite it, let's see what I've got. So what I really have is cosine 2 theta is the same as cosine squared of theta minus sine squared of theta. And that's going to be the same as, so now I've rewritten this thing. And what I've successfully now done is I've now got it all down to the exact same reference angle. So if that's my same reference angle, now we're talking. But now we play the game. I've got all these sines of theta, and I've got this oddball cosine of theta over here. Sure would be nice if I could get rid of that. Well, now let's go up and let's use that Pythagorean identity that I referred to, sine squared theta plus cosine squared theta equals 1. And let's take that thing and let's replace cosine squared theta with 1 minus sine squared of theta. Now, when I look at this, see what I can come up with. Now we've got apples and apples. Now we're talking about all these exact same trig functions with sines. And if you look at this, it looks like we've got sines being squared. It looks like we've got sines being raised to the first power, and it looks like we've got constants. That's a quadratic form of an equation. So let's rewrite this quadratic form of this equation. So I'm going to move everything to the right side. So if I do that, let's see. So the right side of my equation, I'm going to make the left side be a 0. Right side looks like I've got 2 sine squareds of theta minus 3 sines of theta. And then if I subtract my 1 over, it looks like I've got a plus 1. So here's my new equation. It's quadratic in form, which means if it's quadratic, we could use quadratic formula, we could complete the square, or I think maybe we should try to factor this. So if we try to factor it, I'm thinking 2 sine theta in the first quantity, sine theta in the second quantity. Let's see, how about a 1 and a 1? And it looks like my signs are both going to be negative. And if it's a quadratic equation, we're now down to a single term on the right side. If two things are being multiplied to get 0, that would mean that 2 sine theta minus 1 needs to be equal to 0, or sine theta minus 1 has to be equal to 0. So now let's solve these equations. If I rearrange this equation on the left, I'm going to get sine of theta. Let's see, let's add 1. Let's divide by 2. I want to know where sine of theta is 1/2. Sine's positive in quadrant 1, positive in quadrant 2. So if that's the case, I'm looking then for a reference angle. When will sine be equal to 1/2? Well, let's see it. That means it's got to look like this, which means I'm talking about a 30-degree reference angle. So 30-degree reference angle in quadrants 1 and 2. Looks like we're talking about a pi over 6 and a 5 pi over 6. The other equation, let's see. So the other equation, we're looking for when sine of theta is equal to 1. Well, when does that happen? I'm a big fan of using the unit circle. So on my unit circle, let's see. Where is sine equal to 1? Let's see. Sine is equal to 1 at the point 0, 1 on the unit circle. We affectionately like to call that north if we're talking about north, south, east, and west. So the coordinates of the point at north are 0, 1. That 1 is the sine. What would be that angle that would create that value? That would be a 90 at 90 degrees, or we would probably call this thing pi over 2. After all that's said and done, we've got 3 angles that satisfy this equation. So there's your review of identities and solving trig equations.